So anyway, you guys, we've talked a lot about functions. Algebra 2 pretty much is a study of functions, and all we're looking at now is a different type of the many functions we've seen so far. For example, if I wrote this on the screen, take a look. This phrase. Well, now this isn't working. You guys are breaking all my stuff. There it goes. If I wrote this phrase, are you familiar with the phrase?
Quadratic function.
No, we talked about it.
You know we talked about it, right? But if I asked you to write me an example of a quadratic function, could you do it?
I have to go back and look at my notes.
No.
What's a characteristic of a quadratic function?
It has 4 terms.
Is it the one with the x and the x squared?
There you go. A quadratic function has an x and an x squared.
Oh, so these are all the time.
We've seen a lot of these, right? Is this a quadratic function if I erase the x squared?
No.
No.
Yeah, no.
No, a quadratic function has to have x squared.
What's it called?
Technically, it has 4 terms.
Well, the f of x doesn't really. I see what you're talking about. But anyway, would this still be a quadratic function?
Yes.
Yeah, all it has to have is an x squared. That's a quadratic function. Okay? The other connection you need to make is the shape of the graph. Is this the correct shape of a quadratic function's graph?
No.
No.
Is this the correct shape of a quadratic function's graph?
Yes.
No.
Is it a parabola?
What do you think?
No, it's the U.
It's this one?
It's not one.
I thought it was a U because it's squared.
It's the U shape. It's the parabola. Okay? Now, we've talked a ton about this, so we ought to be really familiar. We haven't talked a lot about it, but students seem to remember it pretty well. Absolute value.
Yeah. I'm good with that one.
Students seem to remember it pretty well. What would be an example of an absolute value function? Not a graph, but a function. What does it have to have in it to be absolute value?
An absolute value.
Which is the bars, right? So if I did this, that's absolute value, right? What's the shape of the graph?
V. That's the V.
That's the V shape. There is a reason I'm doing this. You need to be able to tell when I say, all right, we're talking about exponential functions. You need to know what the difference is. And you will after today, but you need to know what the difference between exponential functions and all these other ones. What else have we talked about? Here's one. These students seem to be less familiar with.
Those are the ones that are a little.
Radical, that's
The shape of the graph looks like this. You guys are right. That's the shape of the graph, but what's the function look like? The actual equation. Do you remember what the word radical means?
Oh, it has a radical.
It has a radical. It has a root. So something like this.
like surfing.
Wouldn't that be a radical function? We just actually barely finished talking about another type of function. Rational function. Rational comes from the word ratio. Ratio means
Just
fraction. These are functions that are in the form of a fraction, like this one here. F of x equals x plus 3 over x minus 2. Isn't that in the form of a fraction?
Isn't that what we just did was fractional?
We just did this. We didn't learn how to graph it because they're pretty tough to graph, so
We don't have to
we don't have to graph rational functions. But the point of this, you guys, is if I say a phrase like quadratic function, you should have something in your mind of what that is. Not only a graph, but also an equation, right? Or if I say absolute value, you have something in mind of an equation and a graph. The same thing needs to be true after today of exponential. When I say we're going to talk about exponential functions, you got to have a picture in your mind of what the equation looks like and what the graph might look like. Here's what the equations look like.
Isn't it just a radical with a number with an exponent? Or
There aren't any radicals in it, no. There is an exponent. There is an exponent, but that's the big difference here, because it's not just that it has an exponent. Write this down. This is what an exponential function looks like. F of x equals a times b to the x. A and b are just numbers. That's the big difference. In an exponential function, the variable is up in the exponent. It's not down as a base.
Oh, that's not.
And we haven't seen this before. That's why this is a different type of function altogether. It's not just that it has an exponent. It's that the variable is the exponent. That makes it a completely different type of function. They're not any more difficult. I think they're a little bit easier than most of the other functions we've looked at. And these words I've written on the bottom, this is just terminology. Something in front of a term is called a coefficient. When you have an exponent, it has to be connected to a base. So b is the base, x is the exponent. But I can't tell you how often students get confused with this. Take a look here. This function, is that exponential?
No.
How come?
Because the x sign is not the variable.
Yeah, but students say, well, it has an exponent, so it must be exponential. What kind of function is it? It's quadratic, x squared. What if I wrote this?
Yes.
That's exponential. Because the variable. Do you see the difference? This has a much different kind of graph. It's not a parabola. It's not even really close to a parabola. It's more related to a straight line than it is a parabola. Yeah. But anyway, so that's what the equation looks like. We're going to get into graphing here in a second. There's two types of exponential function, and the names are given. They're primarily descriptive. Thank you. The names are descriptive of the shape of the graph. That would be cool.
See that? It is cubicle. That's my plan for cubicle monkeys.
No, it isn't. Is it really?
Yeah.
Cubicle monkeys? One of the types of functions is called exponential growth. Some of you might have seen this in your biology. Raise your hand if you had biology. Biology? Most of you probably should. Do you remember in biology talking about how cells grow or reproduce? What happens if you have one cell and it reproduces? What happens?
You see it in chemistry.
You get it comes in chemistry too. So you have two cells now, right? Then what happens? Two become four, and then four become eight. Eight becomes 16. That's an example of exponential growth. You guys need to listen carefully. Exponential growth doesn't have a constant rate of change. Okay? Because 2 became 4, but then 4 became 8, 8 became 16, so it's growing at an ever-increasing rate, right? So the shape of the graph isn't going to be a straight line. That has a constant change. It starts with kind of slow growth, and then it expands really rapidly. Exponential growth is what that's called. What else grows exponentially? Your guys' ego grows exponentially. Population growth is exponential growth. Anyway, here's what you need to look at for exponential growth. The base, oh man, we're using big words here. Buckle up. The base of the exponential term is greater than 1. Oh, what does that mean? If b is greater than 1. You see where b is right here? If b is something that's greater than 1, then that's going to be an exponential growth function where the graph starts off relatively flat and then it increases really quickly. Really close, really close. Exponential decay is what it's called. Exponential decay. Matter of fact, just real quick, put your pencils down for a second. I'll have you start writing here in a moment. But you guys are kind of too old to have allowance anymore. But when you were kids, you got an allowance. Some of you probably did, right? It's
I make my age a month.
if you had your choice of these two allowances, okay, what would your? I want you to answer like real quick. I don't want you to think too much about it. I want you to answer right away. if your parents came up and said, I'll give you $1,000 every day for 30 days, or for 30 days, I'll double what I gave you the previous day. So on day 1, I'll give you 1 penny. On day 2, I'll give you 2 pennies. On day 3, I'll give you 4 pennies. On day 4, I'll give you 8 pennies. On day 5, you'll get 16 pennies. So if you had to answer immediately, what would your gut reaction probably be?
Gut reaction would be
Well, most people would say, I'll take $1,000 every day for 30 days. How much money is that? On an average month of 30 days, that's $30,000. Now this is hypothetical. Your parents aren't going to give you that much money. But the point is, you would have passed up a pretty good opportunity. If you got a penny on day 1 and then that doubled all the way to day 30, do you have an estimate of how much money you would have on day 30?
Let's see, 90, I mean, 30 double probably, right? In thousands. 90, 60,
120 grand. Keep going. Keep going. You'd have close to $10 million. Now that's the problem with exponential growth. It seems relatively small at first, right?
Well, yeah.
But what happens after a very short amount of time? It increases by a ton, really quick.
Hey, that's how much money you have.
So
that's what 30 days?
pennies. How did you do the conversion?
That's how many pennies, so like that number.
So divide that by.
So we'd have to divide it in. But so anyway, that's an example of how exponential growth works. It seems like it's very tiny at first, but it gets big pretty quickly. Anyway, the next one's called exponential decay. The way that you tell if a function is going to be decay.
So there's no negatives in this,
Well, the coefficient can be negative,
but the base.
but the base can't. Yeah, well, that's actually a really good point. The base can't be negative. The number in front of the base can be negative, but the base itself can't be negative. You guys might have studied this in chemistry or physics, but does anybody know anything that decays exponentially?
Decay. Let's see.
There you go, radioactive atoms. You guys heard about carbon-14 dating, like how they find out how old things are?
I think
That's radioactive decay, carbon dating. What they measure is the amount of carbon left in something. Carbon decays exponentially over time. That's an example of exponential decay. The value of certain things like automobiles, they decrease in value according to an exponential model. So these are actually pretty applicable types of math. You use these a lot to describe real world things like population growth, bacteria culture, radioactive dating. There's a lot of things that can happen with exponentials. So when you get into college level mathematics where you have to start applying this, then this is actually a pretty popular field of study, exponentials. You use a ton of them. Anyway, to start out with, I'm not going to actually have you graph. I'm just going to have you look at a function and tell me what type it is, and then I'm going to have you plug in numbers into the function. Before we actually do that, though, we need to practice something, because I found my other 2 classes weren't really good at this kind of stuff. I'm mainly talking about A2 again. So let's just really quickly practice some exponents. You guys are probably okay with positive exponents, like 2 to the 2 squared would be 4, but what my other students were having trouble with was negative exponents for some reason.
it's still 4. Well, isn't it negative 4 times negative?
This would be the same. Negative 2 squared would be 4, but 2 to the negative 2 is different.
Negative 8.
Negative 1.
Do you remember that phrase, hop the line, change? Does that phrase sound familiar? Hop the line, change. How does that apply here? Well, there's a fraction line right here. So what if you took this expression and made a hop the line down?
Well, it's not negative 2 over 2.
When it hops the line, it changes the sign. So it's 1/4.
Doesn't change the base.
Nope. It changes the sign of the exponent.
So the one goes to the top row.
Well, there was a,
The denominator, well, there's always a 1.
if you move an entire expression, you have to leave a 1 in its place.
Yeah, 2 times 1 is 1.
Yeah. So you guys, we did talk about this a couple of months ago, but you really need to remember this. Negative exponents don't produce negative numbers. What do negative exponents produce? Fractions, really small numbers. So what about this one then? 2 to the negative 1.
That would be 1 over 2.
That would be 1 over 2 to the positive 1, which is
Just 1 over
1/2. Right? What about fractions raised to a power? What if I had 1/3 raised to the second power? How do you raise a fraction to a power?
2. Don't you put on both?
Those make the fraction, I mean the exponent of fraction.
So then it's
1 over 1.
1 over 9.
This would be 1 squared over 3 squared. The exponent goes to the top and the bottom, which is 1, 9. Or here,
I was thinking maybe like 2 over 1.
well, that's if you have a power being raised to, like if I had x to the 1/3 and that was being squared, then you would, but that's if it's a power to a power. Those you would just multiply. That's, I think, what you were talking about. Here's a real tricky one then. You ready for this one? What if it's a fraction and a negative exponent at the same time in the same wonderful problem? You don't do what Matt said, you do what Sam said. So this becomes 1 to the negative 2 over 3 to the negative 2.
And then it's 3, 2.
And then you flip the line on both sides.
You flip both of them, so this becomes 3 squared over 1 squared. So it's 9.
9 over 1.
9 over 1. So this is just a little bit of prep work for the example I was going to have you do. Were you a little bit more comfortable with fractions and exponents and things now?
Yeah.
All right, try this one.
That one's really hard. I can't do it. 13.5.
Quit it. I just changed it.
Oh, you just have to identify it?
Well, first you identify the type of function. Is this growth or decay? That one should be an easy one.
That's growth.
It's growth because
Because
the base right here is greater than 1, so that identifies this as a growth function. Now, this next part I'm asking right here, find f of 2. What happens with this 2?
Plug into X.
Plug it in for x. This is just practice evaluating. You might be able to do it in your head, but if not, write it down. But this is something you have to do on today's assignment, is evaluate.
Oh, that's easy.
How do you know? I changed it.
27 divided by half is 13.
Wait, where'd 27 come from?
3 to the power of 3.
All right.
3 to the power of 3.
Yeah.
Where's the power of 3 on the 3?
2 plus 1.
Oh, the F is 2. Yeah.
So if I'm asking you to find f of 2, that means this x right here becomes a 2. So
Well, that just confused me because F isn't X. So I get it now.
this becomes 1/2 times 3 to the 2 plus 1 power, because x is now 2. The 2 plus 1 is 3, and then 3 to the 3rd is 27, and half of 27 is 13.5. You guys need to be nicer. You guys need to be nicer to each other.
She's got a problem. She's not unthinkable.
That was decay
I just changed it.
because it's less than 1 and between 0 and 1. Is that a 0? G0?
G of 0.
40. Oh.
Did we identify the type of function? Growth, decay?
Decay. Because it's, oh wait, where's the I?
Between 0 and 1.
The base here is between 0 and 1/3 is a number between 0 and 1, so this is decay. And then G of 0.
Ooh, that's good because then it's negative 2. We have to flip both of them to do much better work.
if this x is a 0, yep, then 0 minus 2 is a negative 2. We just did this. 1/3 of the negative 2?
It's 9.
9. And then 9 times 5?
45.
40. It's 45. All right.
I was cut off someone with McDonald's.
All right, here we go.
Truck.
Okay, we gotta get moving. This is actually the main point of the lesson right here. Take a sec, write that down.
I said I like country, not gonna lie.
Would you rather have about breakups or about sex, drugs, and alcohol?
Disney's not about sex, drugs, and alcohol. Those are.
Who likes 61? Yeah, we are actually. You know we're recording, right?
All right, here we go.
They are currently 24.
The 54 and what?
24.
Ooh, they suck.
You know we're recording, right?
We are recording now.
So our whole
Not bad, I apologize. Country sucks. Yes.
George Strait is 61.
That's not too bad.
Yeah, you probably will.
Anywho,
You?
let's get to this. We're going to graph this function right here, right now. Graph.
What's that? Oh my gosh, I wrote this concept.
Have you seen The Blind Side? Yeah. He's the dad.
Come on. Write it down.
Okay. Wait, hold on. Oh.
F of x equals 2 to the x.
I didn't see the X part.
We're going to work on this together.
I don't have any more paper.
How'd you run out of paper? I don't even have paper.
Okay, since we're not quite sure yet what the actual graph looks like, we're going to just quickly fill out a table of values. Is it okay for x to be that?
No.
No. Yes.
I don't know. I'm asking you guys.
Because the base 0, so that's probably not okay.
Yes, it can be 0.
Yeah, it can be 0.
So what I'm asking is this okay 2 to the 0 power?
Oh, yeah.
Yeah.
That's a good.
No.
What is it though? What is 2 to the 0?
0.
That would make it decay, wouldn't it?
Type in your calculator.
Actually, that would be like a straight line, wouldn't it?
Type in your calculator.
I don't have a calculator like that. Wait.
It's 1.
You know, the calculator.
I don't get.
Yeah, I had
2 to the 0 power
It's 0.
is 1, you guys. We learned that anything to the power of 0 is always 1.
I said 1, though, and it's 0.
Not because I said so. Here's a quick little explanation. A lot of students always ask
0
that.
isn't a real number.
Hey, you guys, listen. Do you guys agree with, to get 0, don't you have to subtract something from itself?
No.
Yes.
Like, isn't m minus m equal to 0?
No.
Well, couldn't you then change that to this? What happens when you divide terms like you subtract their exponents? And what happens when you divide something by itself? You get 1. Anything to the power of 0 has to equal 1 because eventually you're going to end up with this, something divided by itself. It's just something you have to remember. If it has an exponent of 0, what does it equal? 1. Unless it's 0 to the 0. That's something completely different. Anyway, well, we all agreed now that 2 to the 0 power equals 1.
No.
That's our first point on the graph. 0, 1. Let's speed this up a little bit. What about 2 to the first?
Well, you plug it in.
So that's now 2 to the first power, which is
3. I mean,
4.
2.
so 1, 2 is on the graph. Now you guys listen, if all we did was have these 2 points, you would think that the graph looks like that, right?
Yeah, but it's going to change.
But it's not a straight line. The rate of increase is not the same. The rate of increase actually gets quicker and quicker, so the graph is going to have more of that kind of
It's going
shape.
to double, isn't it?
Yeah.
So now it's 4.
So if x is 2, what does this become? 4. Do you see how the rate of increase jumped up?
And then the next one is.
Now the next one's going to be 8. 2, 4,
We only need 3, right?
and then 3,
6. I mean,
So on our test, we only need to write this, right?
Well, you only need a total of 3 points.
And this.
But you guys, this is not the whole entire graph.
Do we have to do
Here and here, that's not the whole graph.
We have to do the table. Don't you have to like put it down to 0?
Well, yeah, we're missing a whole piece of the graph over here. What about if x is -1? Couldn't x be -1? Didn't we just talk about negative exponents?
Yeah. Wait, we need to do points though.
I know, but I want you guys to see what the other part of this graph looks like. Does it look like this?
Isn't it just the
Probably
opposite?
gonna be the opposite.
So like that?
No, it starts at 0 and then it goes up.
Wait, say that again?
Goes up.
It starts
Like this?
pretty much, yeah.
Yeah, I can see that.
Well, let's actually talk about what is 2 to the -1? He's actually right, but let's show it. What fraction? Is that?
0.5.
It's 0.5. So when we're at -1, we're up at a half right there.
Well, yeah, it probably does go flat almost.
What about -2? This is something that a lot of students have trouble understanding. It's a fourth. So we're at -2, we're only at a quarter, which is about right there. What about -3?
1.25.
It's an 8, which is 0.125. So when we're at -3, we're only up in 8. My question is this graph ever going to cross through the x-axis and come down this way?
No.
What if I skipped a couple of numbers and went to -100? Is that going to be,
No, because it's never 0.
it's never 0. It's going to be something really, really tiny, but it's never going to be 0, right? So Sam was pretty accurate. This graph looks like this. It just gets closer and closer to the x-axis without ever actually touching the x-axis.
Ooh, I got it. It's
Right?
7.86. So then E -31.
So that means it has 31 zeros. And then the decimal. So it's a pretty small number, right? Anyway, I need you to draw a dotted line right through here. Draw a dotted line
Over a regular one.
over the x-axis, yes. This kind of behavior, you guys, we haven't seen this in any of our functions yet, but when a graph approaches this kind of a boundary line and then seems to flatten out, that behavior has a name.
How do you pronounce that?
That's pretty close.
It's a total.
The O is silent.
Why would it be the...
Just kidding. I'm just seeing if you guys are trying to pronounce it without wrong. The P is silent. And it's a long A sound, I think. It's the long A sound. No, it's a short A sound. No, it's not that either. Asymptote.
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 Is that the long A or the short A? Or is that the medium A?
Short
I don't know. Anyway, it's pronounced asymptote.
It's like asymptote.
It's Latin. It means not coming together. You see how this asymptote line in the graph, do they ever meet? No. It stays just barely above it. It means not coming together. Asymptote means not meeting.
That's
We're not coming
crazy.
together.
It always goes down, but it will never ever touch it. Ever.
Then you,
Are we ever going to be given a way small fraction that we have to graph? No. Okay.
but the point I'm trying to make, you guys, is if you had stopped and just done this part of the graph right here, I wouldn't have given you full points because the graph actually goes on forever in both directions.
You want to do both sides?
I'll show you later. I'll show you
You
later.
just have to like write it down.
You can just draw it really close to the line and then go through those points that you graph. That's fine. You have to have where that boundary is. It's not always going to be the x-axis, you guys. I need you to listen for just a second. It's not always going to be the x-axis, and here's why. You guys have seen this before. On this graph right here, what does the +3 do to that parabola?
Makes it go up 3.
Makes it go up 3, right? What about this graph here? What does the +3 do to the graph?
Go up 3.
Makes it go up 3. You've seen this a bunch in every single function we've graphed, right? Isn't there something that makes the graph move up or down?
Up 3.
Doesn't that go up 3? Well, what if I had put a +3 out here? What would that have done to the graph? It would move it up 3. So instead of the asymptote being here on the x-axis, where the horizontal asymptote would be? It'd be up 3.
Oh, well, so it's still.
Okay. What if I put a -4 right there?
It goes
It'd
down.
be on the -4.
It'd be down at 4.
But
You guys
it's
see
still
that?
along the.
But it still skims along again. Now, students kind of get
Wait, if
confused.
it's a negative, does that mean it goes up?
Wait, say that again.
If it's a negative, do you flip it? Because it's still.
If there's a negative in front,
Oh yeah, so if it's
upside down.
so right at the top, I would go down.
If this were a fraction,
Well, no, if it was negative.
well, we'll get to decay in a second. But if I put a negative sign in front, that just flips the graph upside down, so it would look like that.
Okay.
Okay? That's if there's negative. We haven't gotten to decay yet. But what I was just going to say is, students get confused with this. That doesn't move the graph up or down. That moves it left or right, because that's inside the function. You see the difference there?
Yes.
If the graph moves left or right, does that affect where this asymptote is? If it just moves left or right? No. So if there are numbers here, that moves where that horizontal asymptote is. If they're up here, that doesn't affect.
Wait, I thought the -4 wouldn't affect it.
If it's here,
Because, like, what if you found out x was 2, and you just combined it, right?
so that again.
Oh no, like if the 4 was up there, next to the x.
Here,
-4.
that doesn't affect the asymptote.
No, then you just move it wherever.
How would you solve that?
For
So,
this one,
Well, I know, but like, if it's like, so
we'll
say
just
x,
choose values of x
say
and
x
plug them
is
in.
2,
but you're
That
never
makes
gonna
it
have a number
-2.
in x when graphing it.
what? That makes it -2, right? And so then why is it
If I plug in a 2 for x,
Yeah.
okay.
We
But I'm
combine it.
never gonna have to.
Well, let's just do a quick little table of values for this. You are going to have to do stuff like this where it's x minus 4. But if
I
x
know,
is 0,
but we're never gonna get a number to put in for x.
well, you have to choose your number.
Right,
Yeah.
so, no.
So you can choose whatever number you want for x. So if x is 0, then 0 minus 4 is -4. 2 to the -4. What's 2 to the -4? We just talked about this. 2 to the -4, you guys.
0.065.
Isn't it a fraction?
It's a fraction. It's 1 over 2 to the 4th.
1/16.
It's 1 over 16. So there's your,
0.065.
that's your y-intercept. It'd be really, really close to here at 0.065.
Oh, yeah. Alright.
You can just choose whatever you want. What if I chose a 2 for x? What would that become?
-2.
That'd be 2 to the -2, which is 1/4. So you can still just graph it that way. Okay, because all that would happen is this graph would shift over 4 units to the right. Anyway, let's do a decay real quick here. All this says is all exponential functions have that asymptote. All of them, every single one. Okay, we're quickly running out of time, you guys, so hustle. We only have 7 minutes.
Yeah.
We're laughing about that word.
No, I wasn't. Stop trying to steal one.
You still is true?
About what? I didn't steal the joke.
Yeah,
You'll never get me.
What was that word he stole? Oh, I have 5. That's right.
I didn't steal anything. I'm pretty sure it's you. I'll just go down to you, Jordan.
Wait, what's that little star?
Let's do this the same way. They all have, every single exponential function has one of those asymptotes.
That just sounds like you put two words together that aren't supposed to go together. Like tote,
Guys.
like a tote bag, it just, I don't.
It's like a fanny pack.
Yeah, I know.
Right?
No, what I'm
Feels like.
That's together.
It's fanny pack.
After
You turn it around, it looks like y'all.
If x is 0, what do we get?
0.
0, so it's 1/2.
You get one!
How many of you were listening 10 minutes ago? Anything to a power of 0 equals?
Oh, anything?
1.
That was the same.
Anything to a power of 0 equals 1. So we have 0.1. That's the point on the graph. 0.1. Now,
half to the first half?
1. Well, I'm guessing the 1/2.
So 1 comma 1/2 is on the graph.
Shoot, so now this is going down. Shoot.
What about if x is 2?
A 4th.
4, yeah, it's a 4.
3 remains.
So do you see how this is a similar behavior, but it's just coming down to the asymptote from the right, from the left to right now? So what do you think is going to happen up in this region?
Really high.
It's really high and it comes down and decreases. This is an example of exponential decay.
Hey, I have a question, Mr. Ralph. Is there any way you could have a 4th and a half?
A 4 1/2. What do you
Like X is a 4.
Well, no. So like it's like 2.5, right? A 4th and a half. Like it's halfway to 1/5.
That doesn't make sense.
Pretty tricky with this fraction.
Let's just not go into this.
Stop listening to Matt.
A 4th and a half would be like. A 4th and a half would be pretty close.
If you added a 4 1/2.
Well, like, let's see. So.
What about -1? This is getting tricky now. 1/2, -1/2. Negative exponents don't make negative numbers.
1.
So it'd just be half.
1/2.
You too.
No, it's
Yeah, it's 2. Like half of it.
Yes, remember the phrase hop the line?
2.
Change the sign. That applies to fractions. Here's a little shortcut, you guys. Listen carefully, please. If you have a fraction that's raised to any, let's try -2. It doesn't matter what the negative exponent is. You guys listening?
Yeah.
Hop the line applies to both of those terms in the parentheses. So they both hop the line, and then you change the sign.
So it's just 4
So if x is -2, then that's going to be 4. We had -1 comma 2, and we had -2 comma 4. You see how this has a similar shape? It's just opposite pretty much. This is an example of exponential decay. You also have to state where that horizontal asymptote is. Just draw it in.
So on this one, it's still at 0.
Because there's nothing here.
So you always want us to draw it where it's at. Okay.
If I had put this on the equation, you guys, what would that have done to the graph?
We would have started it at.
Everything would have gone up 2 units. Would the shape of the graph been the same?
Yes.
Yeah. Everything just moves up 2 units. Okay? So here's actually what I would like you to do when you graph these. This is the long way. All I want you to have is 3 points. So you're going to have 3 points. Every time you graph these, you're going to have 3 points. Plus the horizontal asymptote. So write down these steps real quick. Step 1. Draw.
Is this the last thing?
We have one more quick example to do. Draw the horizontal asymptote. Yeah.
So I've had like 3 different people tell me different things. Do it going before or not going before?
Today we do.
Do it going before.
What the? What? That's crazy.
More time starts tomorrow.
Okay, thanks.
I brought up stuff to work out for trial.
You need to start listening, Gunner. I never ever said it started today.
I thought it was like this week, next week, and week
Well, I said you need to listen better.
Wait, but is it that? But it's not today.
It starts tomorrow.
The
Okay, step 2, plot the y-intercept. All you gotta do is let x equal 0. And then you set that 2 other points. So the y-intercept plus these 2 other points makes the 3 points. Okay? We need to work on this real quick for our last example.
Dang, I didn't write all this stuff.
Well, I'll have you write down as we go. Quickly, we have 1.5 minutes. The first step was to... Was the last example.
Let X equal 0.
What? That's when we're finding our points.
Our little thingy about -5.
This moves the orthogonal axis go down 5. So on the y-axis, go down 5 units and draw that dotted line right through -5. That's your first step.
And then make x equal 0.
And then when you're making your table, the first thing you want is x equals 0. And then all you gotta do is choose two of the points for x.
So
That's it.
1.
1 and 2.
2
Well-
over 1, 2.
So, okay, if x is 0, then 0 plus 1 is 1. 2 to the first power is 2. 2 times 4 is 8. 8
3.
minus 5 is 3. So 0, 3 is a point on the graph.
And then 1, so then 1 plus 1 is 2, 2 is 4, 16, 13.
Close.
11.
11. Very close. Hold on. We gotta finish this real quick. Don't move.
11, not all the way up.
That's really fun.
1 times 11 is right about up here. Now here's what I was getting at. Would it be very wise of you to let x equal 2?
No.
No, because you're going to get a really big number like 29 right here.
So negative 1.
So -1 would be a much wiser choice. Let's do this real quick, then we're done. -1 plus 1?
0.
0. 2 to the 0?
1.
1
One.
minus 4
-1.
minus 5 is -1. Here's what I want you to do. Remember, the graph has to kind of skim along there, and then it increases and goes to boom. Got to go through all the points that you made. There you go.
All right, guys.